Hi friends, good morning, good evening, good afternoon. So if you can hear my voice, can you please write yes in the chat box just to confirm? Okay, okay. So I think my voice is clear. So let's start. So hi friends. So welcome to our next webinar, which is about 5G standalone layer 3 RRC analysis. So many of you have been asking me to show some real life UE traces, UE logs. You want to see a real drive test or post processing tool. How can we analyze the logs? How can we find information about them? So luckily, I got some real 5G UE logs. So what we are going to do today is that we are going to use a post-processing tool and go through 5G UE logs. Therefore, we have to go through level 3 messages, which are the RRC messages. So we will understand each message individually and what is its significance. So we'll try to visualize 5G resource grid as well. So after this session, you should have a very good understanding about 5G call flow, signaling flow, and the network configuration and lots of other things as well. So let's start. And before jumping to topic, I want to say one thing that call flow is not an easy topic. There will be lots of messages and lots of other configuration. So your involvement in the class is critical for you to benefit from this webinar. So I request you, so if it is not absolute necessity, please close all kind of your Outlook, any kind of your Outlook, Facebook, WhatsApp, anything, right? So everything should be closed if possible, because it's proven fact that there is no such thing in the world called multitasking. Even a genius can't do two tasks at the same time. So it's my kind appeal to everybody. Please close all kind of social media or any kind of distraction, right? So please close this kind of distraction. And moreover, I request you please hold your questions till the end. I will take your question in the end, as sometimes answer to your question comes in the very next slide. And moreover, it affects the continuity of the session. So let's begin. So are you with me? So please write yes in the chat box if you are with me, and then we can begin with our first slide. Okay, thank you. Let's begin. So this is a very high level call flow. So in this slide, you see message between user and the radio network during the initial access. So whenever user has to connect to network, it will keep continuously getting the information about the network. For the network, for this network uses sync signals like PSS, SSS, and broadcast channel, which is PBCH, right? So this is also called, I don't know why I'm not able to write, just 1 second. So this is also called, just 1 second, some issue in my this touch screen. Just give me 1 second. I'm just checking where is the issue. Just so give me just one. Yeah, now it's working. Sorry, sorry for that. Okay, so as I said that you can see here message between user and the radio access network. So whenever the user has to connect to network, it will continuously get information from the network. And for this, network uses sync signals, which is PSS, primary sync signal, SSS, secondary sync signal, and also uses broadcast channel, which is PBCH. And this is also called, this whole information is also called SSPBCH block. Okay. So, but please do not worry if you do not understand anything here. It is just a high level. We'll go in detail of every message soon after this slide. So, so now the sync signal helps to identify the central frequency of a particular telecom operator, and it is dependent on the SIM card you are using, right? So they will keep observing these sync signals to identify the center frequency. And once it is identified, it will start syncing. So once it is done, there will be a broadcast channel called PBCH, and the broadcast channel is continuously traveling in the downlink from network to the user equipment, and it also carries all the information that is required for initial access the network. Right. After that, we have this SIB, which is system information block, right? And which are there in the shared channel called PDSCH, and it carries all the information that is required related to thresholds. The thresholds are defined in the network to connect to the network initially, either in the cell selection or you can say cell reselection. There are many parameters in it, but the most important parameter here is QRX level min. We'll talk about in detail later. But the most important parameter in the SIB is QRX level min. And it also gives you information about the PLMN, right? So those all information being transmitted in the SIP block, or you can say system information block 1. So after the downlink sync, there is uplink sync. You can see here for uplink sync, there will be a RACH preamble, right? RACH preamble will be sent. And after this RACH preamble, you can see there is a RACH response from the G0B, and it is so G0B gives back response that says, okay, this particular UE is now allowed to access the network. Okay, so this UE is synchronized with the network. After that, you see here RRC setup request, right? Next message is RRC setup request. So it is a RRC setup request that will come from UE, or you can say user equipment. So here it will take care of all the information related to like tracking area. Also, particular users will be allocated with the help of scheduler, right? So it will see what is the cause of establishment for this particular instance. It will be whether a MO call, empty call, like this. And then we have this RRC setup complete or NAS registration request, right? And after that, we have some kind of ciphering and authentication, and then registration is complete. So this is a very high level call flow. And now we'll go in detail of each messages. Okay, let's begin. Okay. So before going further, we should have knowledge about sync block. So what is sync block? So this is the sync block, which is SS PBCS block. Okay. And it is also called SSB block. Okay. So SSB means sync signaling block. And this is used during initial self-search and the initial kind of access. So what are the things contained in SSPBCS block? First of all, SSPBCS blocks consist of one thing which is called PSS, which is primary sync signal. Then we have SSN, which is secondary sync signal. And then we have this PBCS, right? And all this SSB block require how many symbols? It requires 4 symbols. You can see here 0, 1, 2, and 3, right? So first of all, let's talk about PBCS. So PBCS is transmitted in 3 OFDM symbols. You can see it is transmitted in symbol 1, symbol 2, and the symbol 3. For symbol 1, you can see here it will take 240 subcarriers. For symbol 3, it will take again 240 subcarriers. But for symbol 2, it will leave some of the symbols, some of the subcarriers for the SSS block, right? Then we have this SS, which is consists of PSS, primary sync signal, and the triple S, which is secondary sync signal, right? And the triple S is transmitted in one symbol, you can see, and which we have here, we have 127 carriers. If you count from 56 to 182, and same thing with the PSS, which also contains 127 subcarriers, right? So as you know that we have one thing called PCI, right? And PCI means physical cell identity, and it consists of 2 parts. One is SSS and one is PSSS, right? Secondary sync signal, and the PSS, which is primary sync signal. In case of LTE, if you remember, we have 504 PCIs. But here, in case of NR, we have double the PCIs, which is 1008 PCI. Okay. And here, PCI is equal to 3 into, we have here 336 SSS. But in case of, if you remember in LTE, we have around 168 SSS, right? Plus 0, 1, 2. So we have 3 PSS and 336 SSS, right? So this way PCI is calculated. Okay, let's go in detail about how initial access is done. So we have already discussed that SSB stands for sync signal block and is used during self-search and you can say mobility. And it consists of 3 things, which is PSS, SSS, and the PBCH, right? And it occupies 20 resource blocks and the 4 symbols. So now let's have a look and insight for the self-search procedure. So let's visualize the overall procedure of the sync and the initial block. So once the UE is powered on, UE will start scanning the band to find the SSB frequency location. You can see here how the UE will scan the band. So first of all, it will scan this band, right? Then it will scan this band and so on, so on. Till the time it will find its SSB, which is the at the center frequency, right? It will keep on scanning. So it will do some kind of blind scanning. And after finding the SSB, it will stop scanning the frequency band, right? So this is the first step. So after the UE detected the SSB, it will start decoding PSS. PSS is very easy to decode because we have only three symbols, right? 0, 1, and 2. So after this, it will start decoding PSS. After decoding PSS, it will start decoding SSS, which is secondary sync signal. And with the help of PSS and SSS, the UE will get its PCI, right? Which PCI it has to latch, right? After that, UE will decode PBCH, which is, you know, that physical broadcast channel. So you will do so to obtain and retrieve information related to MIB and the SIB. There are two things which we'll discuss in detail in next slide, which is MIB and SIB. So MIB is the master information block and SIB is the system information block, right? So with the help of system information block, we can get all kind of information like RX level min, RX level offset, all kind of timers like this T300, all these kind of timers will get with the help of this SIB1. Okay. So after the downlink sync signal has been complete, the UE will start what you call PRACH, physical random access channel, right? To complete all kinds of uplink sync, right? So these are the 4 steps we have to follow for initial access. First of all, we'll scan the secondary sync block. Then we have to decode our PSS and SSS to obtain our PCI. After that, we have to decode PBCH to get information related to MIB, and then we will decode SIB1. And after that, we have to start our PRACH procedure. Okay, so these are the few steps we have to do. But if it looks like that there are lots of steps, but these steps will complete in like milliseconds. It will not take even second. So these steps are quite quick in case of LTE and 5G, right? So again, when you first power on your device, the UE doesn't know any idea of which frequency it has to camp on. So it may have to do some kind of blind search. So in 5G standalone, UE is not receiving any prior information regarding the SSB frequency position. And therefore, UE needs to do some kind of blind scan to complete bandwidth until locating the SSB frequency position. So this is how UE acquires our SSB, secondary sync block, which is very important for initial access, right? So the one thing we have talked about is MIB, which is master information block. So let's see what kind of information is transmitted in MIB, which is master information block. So there are many parameters transmitted in MIB. So first thing is half frame index. So you can see that generally frame is divided into 2 parts. One is like first half, and then we have second half. So MIB will decide which half frame index to be provided, right? After that, we have this system frame number. So you can see some system frame numbers are there. So system frame number is also provided by MIB. After that, you have SCS, or you can say subcarrier spacing, right? So subcarrier spacing is also provided with the help of MIB. As you know that in case of LTE, we have fixed subcarrier spacing, which is 15 kilohertz. But in case of NR, we have many options like 15, 30, 60, 120, 240 kilohertz, right? So this kind of information is provided with the help of MIB, like which subcarrier spacing we are using, whether it is 15, whether it is 30, 60, 120, 240, and so on. Then it's also give you information regarding the SIB. So this is the most important information provided by MIB, right? So it gives you the location of SIB. Where is the SIB in the whole grid, right? So it will give you information about the SIB, because SIB is very important. It gives you information about the QRX level min. So MIB gives you information about the SIB1 as well. After that, it gives you information about whether this cell is barred or not. So if cell is barred, you can't you can't latch on this cell, right? So all this information is given by MIB, which is master information block. Okay. And after that, we have SIB, which is system information block. So SIB is very important. There are lots of information provided in SIB, but some of the important information is like, first of all, it gives information related to QRX level. Okay, so this is one of the most important information provided by SIB1. Then it gives you information regarding PLM, right? Or you can say using your SIM, or it gives you information regarding your operator, public LAN mobile network, right? And it also gives you information about some timers like T300, T301, and so on. We'll talk about of these timers in detail in next few slides, but this is the most important information. Like, first of all, QRX level min, then it gives you information regarding the PLMN, then it also gives you information related to T300, T301, N301, and so on, right? N310, and so on, right? So this is the information provided with the help of this SIB1. Okay, so this is again our cell selection summary, right? So as we discussed that the initial cell selection process start with our cell search, and during the cell search, the UE will acquire what you call PSS, SSS, and you can say PCI, right? So if any of these procedure fail, the UE will start acquiring some another 5G cell. So once the cell search is successful, it will check with the help of MIB if the cell is barred or not. If the cell is barred, again, the process will start, right? If it is not barred, then it will jump to SIB. If you know that with the help of SIB, we get information related to PLMN and the QRX level min, right? So with the help of PLMN, the UE check that whether the PLMN matches the PLMN stored in his SIM or not. If it is matches, then it will continue. If it is not matches, then again it will start the process. After that, it will check the QRX level min, right? So if the RSRP measured is more than QRX level min, then it will start latching on this cell. But if that threshold is not met, then it will move back to its own and it will again starting a new cell. This way, it will start camping on cell. So these are the few steps it has to follow before jumping to the cell. Okay, so these are the few things they have to follow for the cell selection process. Okay, friends, let's jump to our 5G resource grid, right? So you can see that over here we have what you call is SSB block, which is secondary sync, which is sync signaling block, right? And you can see here the red one. This red one is the PSS, which is primary sync signal, right? Then we have this yellow, which is SSS, which is secondary sync signal. After reading this PSS and SSS, it will read PBCS, which is physical broadcast channel. And the physical broadcast channel carries the MIB, which is master information block, right? So this one, the purple one, is the PBCS, right? After that, you can see here we have this PDCCS, which is physical downlink control channel, and it is responsible for our signaling, right? And then this blue one is the PDCS, which is physical downlink share channel. And if you remember, this is our data channel. So it is used to carry data between mobile device and the G node. So this is the high level resource grid. And here you can see your PSS, you can see your SSS, you can see your PBCH, PDSCS, and PDCS. Just to let you know one thing, that your RSRP comes from this yellow one, this secondary sync signal. Okay, always remember one thing, that your RSRP always comes from this SSS, secondary sync signal. Okay, and this whole block is called SSB, and with the help of SSB we can get your MIB, which is your master information block. Okay, also we have this DMRS, demodulated RF reference signal. And so this is a brief review of SSB and other things. So let's jump to our post processing tool. So you can see here one post-processing tool where I have loaded all kinds of logs. So it's pretty simple. So if you have a log file, you have to import the log files. So to import the log files, first of all, you have to click on this import function. And after clicking this, you have to import the log files. I'm not able to. Okay. So here you can see here your import option, right? With the help of this import, you can import the file, right? After importing, it will give you option like import log files. So you can see here, we have many options. So you can import the file, which is format you have, right? After getting that, you can just give this one name, like I given the name 5GSA, and you just add files and you will start importing the files. Okay. And after importing the files, just 1 second. Okay. So after importing the files, all the data sets will comes on, you can see here the left side, and all the RSS message comes on this left side as well. So if I right click here, and if I click this show in the message window, then all these messages will become like MIB, RSS request, all these messages will come. We'll discuss all these messages in detail in next few minutes, but in this way, you can load your post processing tool, right? Okay. So first thing we have discussed is the MIB, which is our master information block, right? This we have already discussed, and various kinds of information transmitted in MIB, right? So let's go to focus analyzer and let's see what kind of information is provided in this master information block. So if you click on your focus analyzer, you will see here that in case of MIB, we have discussed that first information is provided is the system frame number, right? So this information is provided in case of master information block, right? So first is system frame number is provided with the help of this master information block. Then it gives you information about the subcarrier spacing, right? Let me change the color. Okay. It also give you information about the subcarrier spacing. As I told you, there are many kinds of subcarrier spacing like 15 kilohertz, 30 kilohertz, and so on. After that, it gives you information about the SIB. So this is the most important information because it gives you information about the location of SIB, right? And after that, it also gives you information about whether this cell is barred or not. If cell is barred, you can't use this cell to latch on. Okay. So let's see. So this is the information provided in case of, and if I go to our tool, you can see all this information will be there, right? So this is information. This is the first message, which is the MIB, right? Okay. So let's talk about. So in simple words, what happens is that if you find out the MIB, then MIB will tell you the location of SIB here. So SIB, for instance, is at this location. You can see here. So with the help of this MIB, we can actually find out the location of SIB1. So now why we need the SIB? Because SIB is very important because SIB carries most of the information that we require to do the network entry or do the attach in standalone, right? So in 5G non-standalone, we do not need this because in 5G non-standalone, the LT tells the UE all about the information to attach. But in standalone, we need SIB1 because there is no LT connection. So the UE is only connected to 5G. And in that case, all the information that is needed to connect comes from 5G. So it reads the SIB, it reads the SSB, SSB gives MIB, and MIB gives you the SIB, right? Let me erase it. Okay. Let's move to the next slide. Just 1 second. Okay. So as you see in the drive test log files, we got the SIB1, right? So here you can see here our SIB1, system information block 1. So this is the information we get from SIB1. So now you can see that QRX level min is the -64. So what does that mean? That -64 actually has to multiply it by 2. So -64 means -128 dBm, right? So it means that UE is allowed to access this cell if the RSRP of UE is above neg 128, right? So if you go back over here to the source grid, so now where the RSRP comes from, as I told earlier that the RSRP comes from this yellow block, or you can say the RSRP comes from this SSS, which is secondary sync signal. The UE measures its power to find out the RSRP. So from triple S, the UE gets the RSRP, and from SIB1, the UE gets the QRX level min, right? So if the value of RSRP is above QRX level min, which is minus 128 in our case. So if RSRP, suppose our RSRP is neg 90, right? But our QRX level min is neg 128, right? So if our RSRP is above minus 128, then UE will think that this cell is a valid cell and we can access this cell and we can latch on this cell, right? So this is how QRX level min, MIB1 and SIB1 is very important, right? For this is required for your initial access, right? After that, you can see that in addition to that, all kinds of information is provided like QRX level min. Then it also gives you information regarding the PLMN, right? With the help of this MCC. Then we have this MNC, which is mobile network code. Also, it gives you information related to tracking area code, right? And in addition to that, it gives you the cell identity, right? Cell identity, as you know, is very important during initial access or all kinds of handover, resource allocation, interface allocation, right? Then we have this NCGI. All this information is provided with the help of this SIB1, right? After that, the next important thing is we need to know the bandwidth, right? So you can see here two parameters. One is offset to point A, and then we have this carrier bandwidth, right? And remember, all these things is coming from this system information block one, right? You can see here little blue one. So all this information is coming from this system information block one, or you can say SIB1. So first thing is the offset to point A. So offset to point A basically defines the frequency offset between point A and the lowest subcarriers of the resource block overlapping with SSB. So what happens is that, so let's see how does it work. So offset to point A, you can see here one thing called offset to point A. So offset to point A tells the SSB location. So basically it tells you the lower edge of the bandwidth, right? And then the carrier bandwidth tells you, you can see here carrier bandwidth, and you can see here one arrow from start to end. So the carrier bandwidth will tell you the total bandwidth of the channel, right? So that's why SIB is very important, because it gives you information related to bandwidth and offset to point A. Also, it gives you information related to tracking area code as well, right? After that, we have these RACH parameters, right? You can see here some RACH parameters, which is RACH is, as you know, that is random access channel, right? And before jumping to RACH, let's see. Do you have any questions so far? Please let me know. I will try my best to answer. If you have any question, please write in chat box, and then we can jump to our RACH parameters. Can you write yes in the chat box if you are getting what I'm saying? Please write yes in the chat box. Okay, thank you. Okay, this is called focus analyzer. The tool we are using here is the focus analyzer. Okay, so let's move to random access channel. So we also get information related to random access channel from the SIB1, which is system information block. As you know that in case of RACH, we have various parameters. So we have parameters related to PRACH parameters like preamble format. Then we have access bearing. Then we have to check that how much is the initial target power, power ramp up, maximum number of attempts, route sequence index. All these information, lots of parameters. We don't have to go in details in these parameters, but all these parameters will be provided with the help of this RACH, right? And these are required for the initial access, right? Let's see from where this green signal is coming. Let me erase. Okay. So the first parameter you see here is the zero correlation zone configuration, right? So zero correlation zone configuration points to a table where this cyclic prefix is obtained. You can see here CS. So CS is the cyclic prefix. So it gives you information related to cyclic prefix, right? Moreover, it gives you information related to route sequence. You can see here, it gives you information related to route sequence. So if your zero correlation zone configuration is 4, then it will tell you that your cyclic prefix is 8 and your route sequence is 1. So route sequence 1 means, so there are various root sequence, right? Where various sequence that is given by like RF design engineer or during the planning at the planning stage. So suppose you have given one root sequence as 1 to one sector. So if you're using zero correlation configuration 4, then it gives you that you can use this and root sequence 1. So it means for second sector, our ratch will be 2. For third sector, our ratch will be 3, right? So there is a gap of only 1 between 3 sectors. But if our zero correlation zone configuration is 15, then it will tell you that root sequence is 8. So if you give root sequence 1 to sector 1, then there will be a gap of 8, right? So our second sector will get ratch of 9 and third sector will get root sequence of 17, right? So this way you can use this zero correlation zone configuration, right? After that, we have various parameters, but here the most important parameter is preamble receive target power. Then we have transmax, and then we have this ramping step, right, which is dB2. So what is this preamble initial receive target power? So this is the initial UE transmit power for the PRATch, which the G node B expects. Again, listen carefully. So preamble receive target power indicates target UE transmit power for the PRATch expected by G node B. So this power is very important. Why this is very important? Because we can't keep this power very high or we can't keep this power very low. So what will happen if this power is very low? So if this power is very low, then it will impact our random access success rate. So suppose this power is very low. Suppose, so right now minus 115, right? And you will start the ratch procedure, right? And after this, since this power is very low, then the ratch procedure will fail, right? So if this ratch procedure will fail, then UE has to start again the ratch procedure, and this way UE has to do the ratch procedure again and again. Since UE has to do ratch procedure again and again, then there will be lots of resources wasted in signaling, and it will affect our random access success, right? So this power can't be very low. But then you think that to avoid ratch failure, we can keep this power very high. We can cap this power minus 90 or minus 95. Even then, that is not a good optimization, because if you keep this power very high, then it will cause interference on your neighboring cells. So you have to optimize this power, right? So generally it is between neg 100 and neg 150, right? Then we have this ratch windows preambles, but there are many parameters like size A, size B, and all these parameters. But then our next important parameter is this transmax, right? So this represents maximum number of preamble transmissions, and possible answer can be 3, 4, 5, 50, 100, right? But here we are using transmax as N100, right? So you must be thinking that if I failing to receive ratch response, how many times I have to try, right? So do I have to try like until the battery runs off, or retry until several times and then give up? So if I have to give up after a certain amount of retry, exactly how many times do I have to retry? So this is done by preamble transmax. So here you can see that our preamble transmax is 100, right? So it means UE tries PRATch retransmit 100 times and then give up. So here you see one more parameter called power ramping step, which is dB2. So it means UE has to increase PRATch power by 2 dB every time it retires. As I said, multiple attempts to access the PRATch may fail due to unfavorable radio condition. So the UE increases the power for random access preambles by a step specified by this parameter called dB2, right? So this can be 0, this can be 2, this can be 4 or 6. So here we have value 2, dB2, right? So 2 dB. So suppose in the first attempt, the power is suppose minus 107 and UE doesn't get any response. So if the power ramp up step is 2 dB, then next time it will transmit at neg 105. Even then, if UE doesn't get response, then it is minus 103 and so on, right? So if our power ramping step is suppose 4 dB, then initially we have minus 107, then it will be neg 103, and then neg 99, right? So it's all dependent on the power ramping step. So power ramping step indicates the steps by which the UE should increase the transmit power, and each time after a RACH access fail. So now, once we have completed our RACH procedure, then we have to go to our next step, which is RRC setup request. Okay, let's jump to our next message, which is RRC setup request. So we have completed master information block. We have completed our system information block. We have discussed the RACH, right? After that, we have this RRC setup request from the UE, right? You can see here RRC setup request. So here we get information related to TIMC, temporary mobile subscriber identity, right? So just to let you know that at this moment we are here RRC setup request, right? It is done by UE to the G node B, right? We are at this step, right? So you can see here that in the RRC setup request, it gives you information related to TIMC, right? Temporary mobile subscriber entry. Other than TIMC, we also get information related to cause of establishment, whether it is MO call or whether it is a empty call. So MO means, you know it is mobile originating, and empty means mobile terminating, right? So when the cause is MO, that means the UE needs to send some data. For instance, if the UE wants to send some WhatsApp message, in that case, the cause will be MO. Now, what happens if the UE is receiving a message? So someone else send a message to UE and you are going to receive it. In that case, you will get a paging message first, and then it will try to attempt to connect to the network. In that case, this cause will be empty, or you can say the cause will be mobile terminating, right? So this is all about RRC setup request. So you see that we have covered this RRC setup request. After the RRC setup request, we have RRC setup done by G node B. You can see here RRC setup complete by RRC setup start by G node B, right? So we are here at this moment RRC setup, right? So now after this we have RRC setup. Now in RRC setup, once the G node B receives the RRC connection step, it sends RRC setup, right? So now RRC setup, you see here one thing called RRC setup. I can show you in the focus analyzer as well, but thing is that when I change the screen, some issue in the Zoom, so I have just taken the print screen. But if you want, just for 1 second, I can show you this focus analyzer. You can see that all these messages are here, right? MIB, we have discussed SIB, we have discussed RRC setup, and then you can see here RRC setup, right? All these print screens I have taken from this focus analyzer only, so you don't have to go to this tool again and again, right? So all these messages are here. So let's move to our PPT. So next message is RRC setup, right? So the RRC setup carries the configuration of the G node B site. Therefore, this message has come. So this message has some of the important configuration that the UE needs to set up the channel. So here we are using SRB1. You see here SRB identity. So if you know that, what is SRB? SRB is signaling radio bearer. So there are many signaling bearer like SRB0, SRB1, SRB2, SRB3. So SRB0 is for initial access, like for common control channel, right? Common control channel. Then SRB1, that is for this dedicated control channel, right? And same thing for SRB2. We don't have to go in detail, but these are the just for your information. We have 4 SRBs in case of G node B: SRB0, SRB1, SRB2, and SRB3. Right. So with the help of RRC setup, we actually set up the SRB1, which is signaling radio bearer 1. Right. So you can see here in the slide that SRB stands for signaling radio bearer. Right. There are many signal radio bearers like SRB0, which is used for control channel. Then we have SRB1, which is used for dedicated control channel, and it is related to NAS message as well. Then we have this SRB2, it is also for dedicated control channel. And this SRB3, this is like unique. It is used for E and DC. If you know the dual connectivity, that in case of NR, we can camp on both UE and G node B at the same time. So at that moment, we have to use this SRB3, right? You can see here various things like T ordering and all these messages. And then we have to jump to what is called RLC, right? So what is RLC? If you know that RLC is radio link control. And the main function of radio link control is related to what you call like flow control, framing, acknowledgement, all these messages. If you heard of one term called ARQ, right? So ARQ is done in the RLC. And if you heard of one term called HARQ, this is done in MAC lane, right? So ARQ is one of the most important function of RLC, which is radio link control. So you see here one term called AM, right? Let's discuss about this AM in the next slide. So RLC can be done in three modes. One is TM mode, one is TM mode, one is UM mode, one is AM mode. So what is TM? So TM is the transparent mode. So this is one of the important interview questions that they ask you, the modes of RLC. They don't go in detail, but at least you know the name of the RLC modes, right? So first one is transparent mode. Then you have UM mode. So what is UM? UM is the unacknowledged mode, right? So UM is the unacknowledged mode. And what is AM? So AM is the acknowledged mode, right? So these are the three modes in case of RLC. And if you see our slide, before going to slide, you can see that ARQ, as I said, ARQ is one of the important function of RLC. And what is ARQ? So ARQ is basically an error control mechanism for the data transmission. It uses acknowledgement. It uses timeout to achieve reliable data transmission. So in short, you can say that ARQ mechanism take care of errors, right? If there is an error, then it discards the package. And after discarding, a new retransmission is required from the sender. So ARQ is an error control protocol. You may have heard of one more thing called HARQ. As I said, HARQ is at MAC layer and ARQ is at RLC layer. Okay. And this is the SN field. So you will see one parameter. So this give you sequence number field. You don't have to go in detail. So even I do not know how this work in detail, but this is our sequence number, right? So again, you can see there are many important parameters here in case of RLC. One is like SN field, T pole transmit, pole PDU, pole byte. All these parameters are transmitted with the help of this RLC layer. But the most important parameter which we use in case of optimization is called the maximum retransmission threshold, right? Let's see how it works. Maximum retransmission threshold. So as we have discussed, this parameter is configured in RLC and its value range is between 1 to 32. So this parameter is used by transmitting side of each AM RLC entity. So what is the main purpose? So main purpose is to limit the retransmissions corresponding to RLC SDU, right? If there is no limit, then G node V will keep on transmitting. And if it is keep on transmitting, then we have wastage of lots of signaling, or you can say we have wastage of lots of resources. To stop wasting the resources, we will give some limit, right? So again, what is the main purpose? So this parameter indicates to upper layers that maximum retransmission has been reached. So therefore, this parameter is used to limit the number of retransmission. So RAS failure will occur if transmission is not successful before expiry of this maximum RTX threshold. Okay, this is the most important parameter. So you can see here maximum retransmission threshold. So here they have given the value 32. So RLC layer will try 32 times before reaching this threshold. Okay, so that's next we have to discuss is the scheduler. And before going to scheduler, please let me know if you have any questions so far. Okay, so somebody asking the session duration. So session will be ended in next maybe 45 minutes. Yes, ARQ is the error detection technique. Yes. So to be truthful, I do not know in which language these codes are written. Focus analyzer use which language? I do not know. Okay, so question comes, how can we improve the accessibility by changing the parameter retransmission threshold? So first of all, as you know that the retransmission threshold has some values like 1 to 32 and maximum value it can take 32. Suppose you have lots of RATch failures, right? And you have given the value 16 in the retransmission. So after 16 transmission, RATch will be a failure. But if you given the value of 32, then it will try 32 times. And if RATch is successful in those 32 times, then you will get the RATch success rate. But in case of 16, it will be failed in 16 and you will get the RATch failure. And as you know that accessibility KPIs is dependent on the RATch success and RATch failure. So if RATch is successful, then our accessibility will improve. If RATch is failure, our accessibility will be degrade. And this way, you can improve your accessibility with the help of this parameter. Okay, sir? Please let me know if you get the answer. Please write yes in the chat box. Our default value is 32 at this moment for the retransmission. Okay, thank you. So if no other question, let's jump to the next topic. So the next topic is scheduler. So what is scheduler? So basically, scheduler decide which of the data should be transmitted, which of the data can wait, right? It works on the priority. For the priority, it uses one thing called logical channel prioritization, right? But we don't have to discuss in detail. But scheduler, the main function of scheduler is to schedule the data, right? Which data should be transmitted now, or which should be transmitted later. And it gives you all the information related to what you call QoS requirement, scheduling, all this information or all these messages are transmitted with the help of this scheduler, right? What are the parameters transmitted in scheduler? So it gives you information related to scheduling request ID, prohibit timer, and transmax. All this information is given with the help of this scheduler, right? So as I said earlier, the scheduler request is very famous word for telecom. It is used for development, testing, and the very important for the optimization engineers as well. The main purpose of scheduling request is to ask for uplink grant to send the uplink data over PUC, right? Or you can say physical uplink control channel. And the uplink grant is sent to UE by G-Node-B over the PDCCH, right? So long story short, we can say that UE initiate the scheduling request to G-Node-B and saying that, hey, I have some data to send. Please give me some grant. Please give me something so that I can transmit the data. So scheduling request is used to notify the G-Node-B that there is data to transmit at the UE RLC. Okay. After that, we have this BSR, or you can say, what is BSR? BSR is the buffer status report. So what is a buffer status report? So buffer status report, as the name indicates, will carry the information on the amount of data available from UE to G-Node. So why is BSR required? So you can see that, first of all, there is a scheduling request, right? And then uplink grant is provided by G-Node-B, right? In this uplink grant, the minimum amount of data or minimum amount of grant is provided by scheduler. Right now, G-Node-B doesn't know how much data UE needs to transmit, right? So it gives you minimum grant and then it will work on. Suppose this buffer status report is not here. Then again, it has to give some minimum data and then again scheduling request. So after that, there will be many scheduling requests if this buffer status report is not here. If there are many scheduling requests, then there is lots of wastage in case of our resources, in case of our signaling. So to stop this scheduling request, there will be a thing called buffer status report. Now, in this, UE will send the amount of data it needs to be transmitted, right? Then only those resources are provided with the help of G-Node. That's why buffer status report is very important to know exactly how much data UE needs to transmit, right? Again, so when scheduling request indication is sent to G-Node-B for uplink grant, G-Node-B has no idea on the amount of data available at UE. So due to this, G-Node-B will not be knowing how much uplink grant needs to allocate for the UE. Also, if the allocated grant was not sufficient, then UE needs to send this scheduling request again and again till all the data is served. And this will take lots of signaling. Also, it will slow the uplink transmission as UE has to send the scheduling request again and again and wait for the uplink grant. So to avoid this delay, BSR is sent in the first uplink grant allocation received after the sending scheduling request. Now, G0B with the BSR info has better understanding of the amount of data pending at UE. So G0B will send uplink grant allocation based on the BSR, buffer status report, without furthering waiting for scheduling request from UE. So this is how this buffer status report works, right? So some of the important parameters here are like periodic BSR timer. So after some time, BSR is transmitted, even it is not required, and then there is a retransmission, right? So these are the few important parameters here in case of BSR. After that, we have one thing called power headroom report, or you can say PHR. So if you know that power headroom report gives you information related to UE maximum transmission power minus push power, right? So you can see here some positive value, some negative values, right? Like neg 23, here you can see neg 34, neg 35, 36, 37, and so on. So what does it mean? So it means if the power is, if the power headroom value is plus, it indicates the UE still have some space under the maximum power, implying I can transmit more data if you allow. But if the UE has negative power, it indicates I'm already transmitting the power greater than what I'm allowed to transmit. So please don't use more than my capability, right? So G0B uses this PHR to estimate how much uplink bandwidth a UE can use for the specific subframe, right? So this is the PHR. The next important message in the RRC setup is the PHR, right? You can see here PHR, right? So you can see here some parameters like PHR periodic timer, PHR prohibit timer, and power factor chain, right? So first of all, what is this periodic timer? So G0B will send information related to PHR after some regular intervals, right? So it defines the interval at which the UE should send PHR reports to the G node B, right? So that the value of PHR determines the duration between consecutive PHR reports. So if you have value 100, then you can say that after 100 subframes, this information will be transmitted again, right? After that, second parameter here is TX power factor chain. You can see the definition below. So this value is a threshold value to report the PHR, right? So what happens? Suppose right now my PHR value is suppose minus 32. Okay, suppose my value is 32, and after that, after some time, my value is minus 31. Okay, so this is the power factor change. So if you are using the power factor change of 1, then we are using power factor change. So what happens is that suppose after some time my value is neg 31, right? So after getting the neg 31, G0B will send a new PHR report. Okay, the new PHR report. Suppose after minus 31, I get minus 30 within maybe 10 subframes, right? Maybe within the maybe within the 10 subframes, right? So will G0B send this PHR again? No. So it will wait for this PHR prohibit timer for 100 subframes. So getting a new PHR, right? It will not continuously transmitting PHR if there is change in the power factor, right? It will wait for at least 100 subframes to send a new PHR, because if you continuously sending the PHR report, it is wastage of our signaling, it is wastage of our resources. So after change in the power factor, suppose minus 32 to minus 31, it will send PHR report immediately, right? Once it will send the report immediately, after getting the report, suppose the power change from minus 31 to 30 in the few seconds. So it will not report that change. It will wait for 100 subframes to report that change. Okay, so this is the That's why this parameter prohibit timer. So here you can see the value of 100. So it will wait for 100 subframe for the next PHR reports to save our resources. Right? After that, we have this RLF timers and the constants. So you can see here some timers like T310, like N311, and these kind of timers you can see here, right? So what are the importance of these timers? These timers are very important because if suppose UE detects a handover failure or RLF, right, then it needs to perform the RRC re-establishment, right? So for performing re-establishment, the first UE needs to select a suitable cell. So it starts some timers. And before expiring of these timers, if UE finds a suitable cell, then UE stop these timers. Okay. But if any of these timers expire before finding a suitable cell, then there is a call drop. And these parameters are very important during the call drop optimization. Let's see how it will work. So you can see here three timers. One is N310, one is T310, one is N311. So N311, N310. So basically this parameter indicates the number of 200 millisecond intervals when a UE is unable to successfully decode the PDCCH due to low RSR. So you can see here we have 4 frames. Frame number 1, frame number 2, frame number 3, frame number 4. So what does it mean? It means if UE is not able to decode 4 consecutive frames, then the timer T310 will start. Okay. So after getting consecutive 4 failures, this T310 starts. So if the value of N310 is 4, it means after 4 frames, then after 4 consecutive failures, T310 parameter will start, right? Then we have this N311, right? So N311 parameter indicates the number of 100 millisecond intervals that the UE must successfully decode the PDCS to be back in sync with the G node. So here you see here 2 frames, frame number 1 and frame number 2. So UE must successfully decode 2 consecutive frames in order for UE to assume the radio link is in sync. So after getting 2 successful frames, this T310 will start. T310 will stop, and our RL radio link failure will not occur, and our establishment will be successful. But before getting this N311, if this T310 will expire, then there will be a call drop, right? Then there will be a call drop, right? This way, these timers will work, right? So again, as I mentioned here that first of all, there will be N310 timer, and if there is a N310 timer, then T310 timer will start, and it will start seeing the N311 times. But before expiring of this T310, if they get the N311, then then the T310 will stop. Otherwise, there will be a call failure, right? So again, upon receiving N310 consecutive out of sync indications, the UE starts the timer T310. And assuming the UE receives N311 in sync indication prior to the timer expiring, the T310 timer will stop. And if not, the timer expires, the UE triggers a radio link failure, right? So you can see here the values of timer like MS1000. So the timer of, so after 100,000 millisecond, this timer will stop, right? And here we can see the out of sync, we have 10 subframes. For in sync, we have only 1 subframe. So after getting 1 subframe in sync, our timer will stop. So it needs only 1 in sync in this case of drive test logs. Then we have this PDCCS configuration. So we also have the PDCCS configuration. So here you can see the DMRS configuration as well, right? So this RRC message tells you about the PDCCS, DMRS as well. So one of the most important parameter here is the monitoring symbol within the slot, right? You see here the monitoring symbols within the slot, right? So UE needs to find out which PDCCS symbol should be on, right? So whether it will be 1 symbol, 2 symbol, or 3 symbols. If you remember, for PDCCH, maximum you can use is 3 symbols, right? So we have to know that for this configuration whether GNodeB is using one symbol, two symbol, or three symbols, right? So with the help of this parameter, monitoring symbols within slot, we can see how many symbols are used for PDCCS. If you remember, we have seen that the value is 1 and then we have 13 0, right? What does it mean? You know that we have 14 slots, right? We have 14 slots. You can count here like 1, 2, and you can see 14 slots from 1 to 14, right? So this first slot is for PDCCS. And how do you know that this PDCCS? Because in the parameter monitoring symbols within slot, we have these values, right? 1. So 1 is for PDCS and rest. So if the value here is like 1, 1, 0, 0, and so on, then first two slots are reserved for PDCCS, right? So this indicates the UE will only have to look at the first symbol that will carry the PDCCS. So this way we understand the PDCCS as well, right? So then we have these aggregation levels. We don't have to go in details. So aggregation details is also given by this, right? So this is all about RRC setup. You see here we have called the RRC setup, right? So in the RRC setup, what we have learned, so in RRC setup, GNode will receive the RRC connection request. It sends the RRC setup, which carries the configuration of GNode. If you remember what we have learned here, we have learned here information related to SRB1. Then we have discussed about the RLC layer, right? We have discussed here 3 modes. One is AM mode, one is TM mode, and one is UM mode. Then also we have discussed information related to schedulers, right? After that, we also discussed buffer status report, right? After that, we have gone through power headroom. Then we have discussed our RLF timers and the BDC. So all this information is given in this small message, which is RRC setup, right? So all these parameters are given in the RRC setup. So RRC setup is one of the most important parameters, right? So after this, the UE uses RRC setup complete messages to configure it with all the parameters. Then it sets RRC setup complete message. You see here, right? So it carries the information which actually tells the GNodeB that all the configuration that GNodeB has sent has been configured. So RRC setup complete message can also contain like information related to NAS, right? For instance, if there is an attached request, that is a NAS message also inside the RRC setup complete, right? After this, you can see here we have many things like we have authentication, we have security mode command, we have UE capability inquiry, right? And then all these things are done here in this, right? So with the help of this code, right? So here you can see the security mode mode command. These parameters are sent, right? Then you see the UE capability, right? So you can see here the UE capability. So whether this UE is capable of NR or not, you can see here RAT type, right? Radio access type, right? So here you can see that this UE will support the NR. In addition to NR, this UE will support EUTRA, right? It means dual connectivity, right? If you heard the term ENDC, right? EUTRAN, NR, dual connectivity. So this mobile will support 5G as well as UE, right? So it means it can support both, right? And then we have this DL, right? So then we have this RRC reconfiguration, right? You can see here RRC reconfiguration. So as you guess from the word itself, the major functionality of RRC reconfiguration is to modify RRC configuration. So this implies that there should have already been some RRC configuration process before this message. So now we have RRC connection reconfiguration. So here we have to set the RAB, radio access bearer. We also have to set the DRB, which is data radio bearer, right? So it has information about the PDU, right? It has information related to DRB. So here in the RRC configuration, the DRB is also set. So you can set this point where more or less we have attached to the whole configuration, right? So in RRC reconfiguration message, you also get information related to your mobility. You know that we have various kinds of mobilities like A1, A2, A3, right? Then we have B1, B2, and so on, right? So it gives you information related to A3 parameters as well and other kinds of parameters, right? As I said, we have various kinds of handover events it can be A1, A2, A3, A4, A5, and so on, right? So let's talk about one out of these one event A3, which is one of the most important event. So event A3 is triggered when a neighboring cells become better than the serving cells by an offset within time to trigger period. So what is the condition for A3 event? So A3 event tell you that the RSRP of the neighbor should be more than RSRP of the serving cell. Only then handover will happen. In addition to that, we have few parameters like hysteresis, right? You can see here parameter called hysteresis. Then we have this parameter called offset, right? These are two additional parameters. So why we need these two parameters? First parameter is offset. So this parameter indicates serving cells should be better than neighboring cells before going to set the measurement report. Suppose RSRP of neighboring cell is minus 90, and suppose RSRP of serving cell is minus 91, right? And minus 90 is more than minus 91. And you will think that handover will happen. No, handover will not happen immediately. There will be offset. So suppose there is offset of 2 dB, right? Then actual value here is minus 89. So handover will not happen, right? Because the neighbor value is neg 90. Then the second parameter is the hysteresis, right? So this parameter indicates neighboring cell should be better than the serving before going to send the measurement report. Suppose hysteresis value is minus 2, right? Then here it will use minus 90 minus 2. So actual value of neighbor RSRP is neg 92, not neg 90, right? So this way we can avoid handover immediately. Then we have this parameter called time to trigger. So this parameter is used to avoid ping pong handover when measuring the power levels. So these three parameters are very important for the mobility optimization, right? And you can see the A2 parameters also here. You can see some A2 parameters, right? So let's recall what we have learned. I want to change this window actually. How to change this? Just 1 second. Okay, now it's okay. Okay, let's recall what we have learned. So we have learned that. First of all, when U is power on, right, it will do the self search and it will decode the MIB. Then it will store the decoded MIB. After decoding that, it will check whether cell is barred or not. If cell is not barred, then it will move on to the next step. And using the parameters in MIB, it will try to decode the SIB1. Right? So if I have SIB1 decoding is successful, then it will store the information and then it will move to the next step. Right? And we have discussed about the SS PBCS block. We have discussed that we have many signals like PSS is there, SS is there, PBC is there. And with the help of that, we can create our PCI, right? And with the help of this PBCH, we can get our MIB. With the help of MIB, we get SIB1, right? And we have also discussed this grid. And in the grid, we have discussed that where is the location of PDSCH, where is the location of PDCCH, DMRS. Then we have discussed offset to point A, carrier bandwidth. All these things we have discussed during our webinar, right? After that, we have discussed in detail call flow also. Like first of all, MIB information is sent by G node B to the UE. And after that, SIB information is transmitted. Then UE is sent for RAG preamble, right? And after RAG preamble, RAG response is provided by G node B. Then we have RRC setup request. And then RRC setup complete message by G node B. Then RRC complete plus NAS registration by UE, right? And this message for, right? There are lots of messages and lots of parameters there in the RRC setup request and RRC setup, right? After that, we have ciphering, right? We have authentication. Then we have UE capabilities, right? So all these things will be done here with the help of this code. And after that, we have RRC reconfiguration complete message, right? So this way, our data radio bearer will be set. And now you can actually transfer the data between UE and the G node B and the core network, right? So now overall, this is how the tool look like this, right? So how the signaling process look like, right? So I just want to give you a flavor of how we can use a real post-processing tool. In more details, it will be in my training, in my paid training. So it is just 9.99 for only the people who have attended this webinar. So please enroll for that training and you will get more details in that course, right? Okay, friends. Okay, friends, if no question, again, thanks a lot for giving me your precious time and thanks a lot. Bye.